5-8 is all about scale drawings and models. So it says a scale drawing or scale model is used to represent an object that is too large or too small to be built or to be drawn or built at actual size. So we see scale drawings a lot and scale models a lot in science. Things like planets are too big, so you will see models or drawings of planets. Or like molecules, things like that. They're too small, so we see models and drawings. Maps are a good example of scale drawings. Blueprints, in order to create the plans for a building, are scale drawings. It says the lengths and widths of objects on a scale drawing or model are proportional to the lengths and the widths of the actual. So when you create these models and drawings, you have to create it proportional to the actual in order for it to be useful, okay? There wouldn't be a point of having a molecule drawing or model that isn't proportional to the actual thing, because it wouldn't give us a good idea of what it actually looks like. So it needs to be proportional, just like on a blueprint. If we would make our blueprint and we don't make it proportional to the actual amounts that we're going to use, when we start building, we're going to have issues and we're going to be confused and not have the right amounts of things and things like that. It says the scale is determined by the ratio of a given length on the drawing or model to its corresponding length on the actual. Consider the following scales. So 1 inch is equal to 3 feet. That is a scale here. When we do the scale, it is always model to actual. Model to actual. Even when we write our fractions, it's going to be model over actual. So like on this one, when I would write it as a fraction, I'd put 1 inch over 3 feet. On this one, I'd do 1 centimeter over 2 millimeters. Model to actual. Okay? On example 1, it says, suppose a model of a dragonfly has a wing length of 4 centimeters. If the length of the insect's actual wings is 6 centimeters, what is the scale model, or the scale of the model? So the first part tells us the model is 4 centimeters. The actual is 6 centimeters. So we do our model over our actual. And then since it wants the scale, remember your scale is going to look like this. Whatever it is on the model is equal to this on the actual. Whatever it is on the model is equal to this on the actual. And notice the model, when we do a scale, it's always 1 of something is equal to what it would be on the actual. So that's where our 1 came from. When we're doing a scale, we always want 1 for our model. So we put our 1 in, we put our x, and then we do our cross products. 4 times x is 4x, 6 times 1 is 6. Divide by 4 on both sides, and you get 1.4. So we know when the model is 1 centimeter, the actual is 1.5 centimeters. So you actually have to write that out for your scale then. This is the scale. Your answer wouldn't just be 1.5 centimeters. The scale is that 1 centimeter in the model is equal to 1.5 centimeters of the actual. So an example of this, it says the pillars of the World War II Memorial in Washington, D.C. are 17 feet tall. That's the actual. A scale model of the memorial has pillars that are 5 inches. That's my model. What is the scale of the model? We always do model over actual. So my model was 5 inches. My actual was 17 feet. And for my scale, I always want 1 of whatever label is on the top for the model, and we figure out the bottom. So 17 times 1 is 17, 5 times x is 5x. Divide by the coefficient on both sides, and x is equal to 3.4. So that means for my scale, it would end up being 1 inch is equal to 3.4 feet. So this would be my answer, not just that there. This is how you would write a scale. The next thing that we're going to talk about is scale factors. Okay, it says, if a scale drawing and a model have the same unit of measure, the scale can be written without units. This is called a scale factor. This is really similar to when we were talking about ratios, and we'd have something like 2 pints to 1 gallon, and we'd have to change our gallons into pints, and then we could take our labels off and compare just the two numbers. Okay, we're doing the same thing with the scale factor. If the scale is 1 inch is equal to 2 feet, just like we found a scale here, we do our model and our actual written as a fraction. So it'd be 1 inch over 2 feet. I need them to have the same label. It's always easiest to go from the biggest to the smallest, so times 12 would be 1 foot is 12 inches, so 2 feet is 24 inches. Once you have the same label, you can cancel them out, and it's just 1 to 24. So it says 1 unit of the model represents an actual distance of 24 units. So the model's length is 1/24th the size of the actual object's length. So scale factor is just changing it so that it has the same units and then writing it as your factor here like this. Okay? Sometimes I've seen it written as a fraction as well, so either one really works. Like this one, if I wanted to change this into a scale factor, 1 inch over 3.4 feet. I'm trying to change it into inches, so I would have to times by 12. So it would be 1 inch over 40.8. So it would be written like that. Okay? So they have to have the same label, and then you take off the label at the end. The blueprint of a scale or skateboard ramp shows that the length is 11.4. Since it said it's a blueprint, that is my model. If the scale of the blueprint is 1 inch is equal to 6 feet, remember we always do model to actual, what is the length of the actual skateboard ramp? So I'm looking for the actual here. So this becomes really easy to set up if we're doing model over actual, model over actual. The easiest way to do it is to find the scale that they gave you. They gave us 1 inch is equal to 6 feet. Always put that in the first fraction. 1 inch is 6 feet. Then put in your other number in for the model, put in your x for the actual. Do your cross products and solve. 6 times 11.4 is 68.4. 1 times x is just x. There is a second way to do this with an equation. You can take the time to look through that in your notes. I'm not going to go over it because I don't expect you to use it this way, but just like how in the last lesson we did proportions and then we did equations, you can do your scale drawings and scale model problems with proportions or equations. I just think the equations is easier, so we're going to skip method 2. Got it 2 says a map of a natural history museum shows the dinosaur exhibit room is 7.25 inches wide. If the scale on the map is 1 inch is equal to 8 feet, what is the width of the actual exhibit room? So we have our proportion. We're doing model over actual. Again, the easiest thing is just to take that scale and put it in that first fraction. It's always model over actual. Then when I look at it, this is talking about 7.2 inches. Well, if the inches are the top, I know inches have to be on the top here. The other thing you can do is notice it was talking about a map. A map is my model, where I want to find the actual. So 1 times x is just x, and 8 times 7.25 is 58. Make sure you label. It's 58 feet. 58 feet that we are talking about. The last thing that we're talking about is finding dimensions. Dimensions mean like my length and my width, using proportions, and then using it to actually create a scale drawing. So like this one says, Lila is painting a mural at the community center on a wall that measures 18 feet long and 12 feet tall. Make a scale drawing of the mural. Use a scale of 1/4 inch is equal to 3 feet. That's our scale there. And it says use 1/4 of an inch grid paper. So we can kind of ignore that part for now. So we have our scale. We're going to have to do two different proportions, one for length, that's what they did in step 1, and one for width. That's what they did in step 2. In both of them, they're using that scale of 1/4 of an inch equals 3 feet. That makes up that first half of the proportion there. The other half is 18 feet long was our actual length, 12 feet wide was our actual width, and then we put our variables in. They did their cross products and solved. 1/4 times 18 is 4.5, 3 times L is 3L. You solve and you get 1.5 inches. Here, 1/4 times 12 is 3, 3 times W is 3W, divide by 3 on both sides and you get W is equal to 1. So we know it's going to be 1.5 for the length and 1 for the width. To make our scale drawing now, it said it wants us to use 1/4 of an inch grid paper. Well, 1/4 of an inch, that's 0.25. So it's kind of like counting by quarters of an inch. So if I need to get to 1.5 inches, I'll go, okay, 0.25, 0.5, 0.75, 1, 1.25, 1.5. That's 6. So I'm going to need 6 squares on our grid paper. If it's 1/4 of an inch for each one and I need to get to an inch, that's 0.25, 0.5, 0.75, 1. So that's 4 squares. And below you can see that they made that scale drawing, and they said it went 6 across for the length, 4 down for the width. Okay. We have one got it problem to try with it, and then that's the end of this. So it says an architect is designing a school courtyard that is 45 feet long, that's the actual, and 30 feet wide, actual. Use a scale drawing, or make a scale drawing of the courtyard. Use a scale of 0.5 inch is 10 feet. And then we have our grid paper size that we're going to be using. Okay? So I know that I need length and I need width. On both of them, when I go to solve, I'm using this as my scale, 0.5 inch, 10 feet, 0.5 inch, 10 feet. Then, these are my actual, this was my length, this was my width. I'm trying to find the model in each one. I do my cross products, 10 times x is 10x, 0.5 times 45, that's 22.5. Half of 30 is 15. I divide by 10 because it's the coefficient in both equations. And x is equal to 2.25 inches. Here, x is equal to 1.5 inch. Okay? So 2.25 and 1.5 inch, when we go to use the 1/4 inch grid paper, well, when I count, again, I've already done 1.5, but 0.25, 0.5, 0.75, 1, 1.25, 1.5. That's 6. On this one, 1.25, 1.5, 1.75, 1, 1.25, 1.5, 1.75, 2, and then 2.25. That's 9. So we'd go 9 squares across, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 6 down. 1, 2, 3, 4, 5, 6. You just finish off that rectangle then. Let me know if you have any questions.